We are going to be using a C4. We're going to be using TNT. And then we're going to be using the linear detonation velocity detonated from the origin. And then, yeah, it's expanding into air. I don't think we have. So we're going to be calculating the impulse and overpressure, and then we're going to be looking at the max values of those. And we're going to be sampling those after the fact to get the fields we need. We also have this time of arrival function, which basically uses the max pressure, and then as well as some probes. So what this gives us So here we have the maximum overpressure scene. You can see match very well. Then we'll look at the impulse. Matches pretty well at the later, longer distances. Up close, you get a lot more numerical effects. And then finally, we're going to look at the time of arrival. And match pretty well. So these were all done using just some other OpenFOAM post-processing utilities, specifically post-process. Basically, we create a line, we sample it, and then we output some CSV file or numerical data that gives the location as well as the values of given fields. So that's what we use for this. Yeah, again, this case, if you're interested in it, it's in the repository under the validation. Peter, did I miss anything?
No, I think that was great. If there are some additional questions, I know in the chat, Liang was asking about maybe a little bit more background on PREF, Jeff. How that's utilized or not, depending maybe on the activation model, if that's the case.
Oh, specifically for.
So I can read the question. So the question was, just as a follow-up on PREF, as you mentioned that PREF is the unreactive.
Oh. Yeah, sorry. PREF is, so it's different. I believe it's called PREF in here as well, right? Yeah, so that is a different PREF. I'm sorry for that confusion. So PREF in the blending is basically just the pressure of the surrounding fluid. Solid state. So that you can think of that as P solid. So that's calculated using an equation of state. It's not a constant value. So you would get that for the blending, you would get that PREF from, say, the Murnaghan equation of state or the Cochran-Shannon or something like that. The PREF here is essentially your atmospheric pressure. So this is, nothing is happening. You have no pressure gradients. This is what you would want to use for your reference pressure. Basically, it's just something so you can see your overpressure and calculate that. So they are different. I apologize for the confusion.
No, that's great. I guess if there are, I don't know if there are any additional kind of questions we might be able to go over. We have just a few minutes left. If not, or if questions come up later, I mean, feel free to reach out. Jeff, can you put up the final slide with the contact information?
Yes, sorry. Yeah, and in response to the mass fraction, So basically what you would want to do with that is, so for two-phase simulations, you only have one volume fraction, but the other one is just one minus that volume fraction, which is why we only have one, because there's no need to care about both.
But if you have more than two,
then you have to sum all of them.
Exactly. So they'll all sum one, but they'll be explicitly treated.
And the row field is the volume average of all of them. So that's automatically been added altogether. So that's been done.
Yeah, and I think some of the background on that too, if check out the user guide. That does have more detail on on where and why we implemented these schemes as we did. So you can go back even further in the literature and see some of the references that we used and really built upon and in some cases implemented explicitly as part of this. The structure of the solver is a little different from other OpenFOAM solvers from a source code perspective, mainly that it includes some ODE solvers for time stepping so that we can have things like fourth order time integration and much more sophisticated and robust explicit schemes. The advantage is they're much more stable. But if you're used to looking at other OpenFOAM solvers, you may find, and from a source code perspective, you may find things are structured a little bit differently.
They're weird.
Yeah, they're a little weird, but they are logical, and I think it's fairly simple to follow along, particularly if you're familiar with like Runge-Kutta schemes and some kind of ODE-based time integration.
Yeah, which is why everything's done in the compressible system, because it has to be virtual for the ODE integration.
That's right, exactly. So I think I'll summarize the course and we'll close it now. So basic takeaways: BLASTFOAM case structure, same as any other OpenFOAM case. Okay, check out the constant system directories. Everything is exactly as it would be with any other OpenFOAM solver tutorial. The phase properties file is where all the magic happens in terms of the reactions, the different equations of state, where we apply the coefficients and how we define how those, how the products basically turn into and expand as reactants and interact with the surrounding medium. And that's the model problem that we went over. Specifying initial and boundary conditions, the kind of numbered directories, that's where you're going to find boundary conditions. There's a lot of tutorials and a lot of validation examples. So chances are, if you want to run a problem that's a little different than you saw today, using those and then modifying those cases is typically a pretty easy way to go about it. So make incremental modifications. That'd be my suggestion. Incremental modifications, change out the geometry, see what happens. Change something else, see what happens, is a nice way to get started and use those as a springboard going forward. We also covered how to kind of run a BLASTFOAM or really any OpenFOAM simulation from, as a series of utilities, right? Read some geometry, create a grid, modify that grid, set some initial conditions on the grid, set your boundary conditions, run the code, and look at the output in post-process. A lot of the validation cases have a little extra post-processing built in there that automatically does the comparison with the known reference solution. Those are in there. They're really useful. Modify those to use those too, especially if you're doing a lot of numerical work or doing something kind of new. That can be really handy. We also covered where we add the probes, other kind of post-processing in that control file. Again, we have a few additional utilities that make things easier and really are focused on high explosive detonation type post-processing. Some of the things like calculating impulse and outputting overpressure, they're mainly convenience functions, but they of course are convenient and useful for this type of problem. We went over a little bit about specifying numerical schemes, not too much, but again, these tutorial cases provide some kind of best practices, and the validation cases are also really useful for seeing which particular numerical options were used and perhaps why, and what the effect of those would be on attaining a reference solution. We went over how to view the results. So what that means is we're using peer review. There's nothing new, nothing exciting, nothing different. It's just peer review. You load that .foam file. It tells peer review, hey, I need to open an OpenFOAM case. BlastFoam is just, it's just an OpenFOAM solver, if you will. The structure is the same. So if you can run BlastFoam, you can run any other OpenFOAM solver, and conversely, if you can run OpenFOAM, BlastFoam, you should feel right at home with it. Where do we go next? What's coming up? From a development perspective, you're going to see more fluid structure interaction. You're going to see more advanced particle methods. We're going to see reacting particles. We're going to see particle-laden flow. We're going to see quadrature-based moment methods coupled with BlastFoam to do some really interesting things. They have a lot of utility in industrial kind of accidents and prediction, certainly utility in modeling non-ideal explosives, thermobarics, and that will become, so that will be the subject probably of a more advanced course, and was meant to be the subject of a paper and a presentation this year, albeit all the conferences got canceled. So bummer, but we're still gonna release the code and we're still gonna try and support it, if not in person, virtually. Where do you get help? First, go to the user guide. The user guide's great. It's very complete. It's concise. It's readable, and the information is there. As Jeff mentioned, there's a few additional updates and utilities that have come out really in the last couple days. So we'll have that user guide updated probably in the coming week. So it will be current. But refer to the user guide. The user guide's great. References to anybody else's projects that we used, a fantastic AMR library that this German group produced. Absolutely great. References in there, reference to their papers in there. Read it, look at it, use it. It's fantastic. The GitHub repository, again, we update the code pretty much continuously. Certainly if we find any bugs, we do those fixes as a priority. And also take feature requests, etc. So that's a great way to get in touch, communicate, report issues, bugs. And if you have some code to submit, please throw a pull request up there. We'd be happy to review it, and if we can incorporate community contributions to the code, we would love to do that. As we said in the beginning, we really think of this as your code. It's not our code. We want this to be something unique and something that really contributes to the community, which I think has been kind of underserved or served a bit differently maybe, as at least from an open source solver perspective. And then finally, if you have some other questions, interested in follow-up, want to do a more specific bespoke workshop, maybe for yourself or your team, whatever, feel free to get in touch, info@synthetictechnologies.com. Happy to answer any questions. And yeah, thank you everybody for your time. Thank you for attending the workshop. And again, any follow-on, please get in touch. And yeah, I hope you're all successful in running BlastFoam, and I hope this was useful.
Yeah. Peter, you want to hang on for a little bit, just see if anyone else has any questions?
Sure. We'll hang out for a little bit and take any questions in the chat. Thanks, everybody.